Alrighty, howdy folks. The next thing we are going to look at is Taylor and Maclaurin series, and this will be the final thing in this sequences and series chapter. And Taylor-Maclaurin series is how should I put it? It's so beautifully important. Oh boy, you can do a whole bunch of things. And this is one of those concepts that you will see a lot, even in future. Like if you happen to be an engineer somewhere or the other, people will say, "Oh, I just used a Taylor series expansion of it, and do this one." Okay, cool. So let's get on with it. As a motivation for this, I need to start off with something simple. First, what kind of a series is this? 1 plus x squared plus x cubed plus so on. Right? Does it look familiar to you? 1 plus x squared. What all series did we learn about? Can I refer you to the GHTP? Geometric Harmonic Telescopic P series. Does this look like any one of them? It does. It's actually a geometric series because notice we start with a 1 and the next term we multiply by x and we get x, and to get the next term we multiply this guy by another x, and so this is a geometric series, right? With r being equal to x. So try to recall, when does a geometric series converge? Whenever the absolute value of r is less than 1, right? So that means the absolute value of x, whenever absolute value of x is less than 1, this series converges. Are we cool with that? Okay, there's one more thing I want you to recall if you can. What is the sum of a converging geometric series? Here, notice, you remember, maybe I'll put it this way. So what's the sum of a converging geometric series? A over 1 minus r. What is a here? 1. R is x. So, and the sum is just 1 over 1 minus x. Right? Of course, the condition is that absolute value of x must be less than 1. X cannot be whatever value it wants to be, right? X, as long as x is between -1 and +1, we can say that 1 plus x squared plus x cubed, all of this is equal to 1 over 1 minus x. In other words, if we can think of 1 over 1 minus x as a function of x, okay, f of x is equal to 1 over 1 minus x, and that is equal to this. And we can say this. In sigma notation, we can write this as sigma n equals 0 to infinity x to the n. And that is the coolest thing next to sliced bread. What? I know, you're thinking, what? You just wrote a stupid 1 over 1 minus x as sigma. What's the big deal about that? Now, the big deal about this is, here is a function 1 over 1 minus x that could be written as a power series, right? Some function 1 over 1 minus x that could be written as a power series. And this started a whole big revolution in mathematics. Okay, if I can write 1 over 1 minus x as a power series, what about some other function? Could I write 1 over 1 plus x? Yeah. As simple as, can other function be in a similar way? Yeah. Well, recognize that 1 plus x can be written as 1 minus negative x. Now, does it have the same form as 1 over 1 minus x? Yeah, the only difference is instead of a x, we have a negative x. So we can write this as 1 plus negative x plus the quantity negative x squared plus so on like this. In other words, we can write it as this. Would you agree this is a power series? N sigma n equals 0 to infinity, negative 1 to the n, x to the n? Yeah, it is, because it is in the form of sigma n equals 0 to infinity c sub n x minus a to the n. A happens to be 0 here. So c sub n is negative 1 to the n, and a happens to be 0. So we could write another function called 1 over 1 plus x as a power series. Having started with 1 over 1 minus x as a power series, we got another function that we could. So this, now it's like an avalanche, you know. The whole, okay, how about this one? Yeah, apply the same concept, 1 over 1 plus 2x squared. Write it this way. And, yep, that can be written as a power series. This time c sub n happens to be negative 1 to the n, 2 to the n. Cool? All right. So far, everything seems to have that form of 1 over 1 minus x, right? Is that all? Is that the only thing that you can write? Did a function that that is in the form of 1 over 1 minus x, but for x you can have something else? No. It could be, now watch this one. This is fairly interesting. Can I differentiate this? Yep, df dx, the derivative of f of x is the derivative of 1 over 1 minus x. Can you quickly calculate as to what the derivative of 1 over 1 minus x is? Chain rule. 1 over x, the derivative would be negative 1 over x squared. So 1 over 1 minus x, trust me, would be negative 1 over 1 minus x, the quantity square, times negative 1, chain rule, making it positive 1 over 1 minus x squared. Okay, so what's the big deal about taking the derivative of this? Well, since this is equal to this, we could say the right-hand side, this must be equal to the derivative of that expanded version of this power series. Because after all, we claimed that f of x equals 1 plus x squared plus x cubed, right? So we'll take the derivative of that and we get this. Can you guess as to what the big deal about this is? Yeah, the big deal is we have another sort of completely different kind of function, 1 over the quantity 1 minus x squared, expressed as a power series here. Okay, now what is c sub n? C sub n is n, provided n is an element in the set, natural number set 1, 2, 3, 4, 5, 6. Right? Okay. Buoyed by all of this. Okay, there are some functions that can be written as power series. Somebody said, okay, how about e to the x, sine x, cosine x, all these kind of functions, can we write them as power series? And in fact, when you actually get to differential equations, a differential equation is basically, let me say, dy dx, dy over dx is equal to x. Okay, that's a differential equation. What is the solution of the differential equation? Apparently dy dx must equal x. The derivative of some y must be equal to x. So what should y be so that dy dx would equal x? Would you agree 1/2 x squared? 1/2 x squared plus some constant. We could add an arbitrary constant to it, right? So a solution of a differential equation is also a function. Now we just saw that some functions can be written as power series. So when we try to find the solution of a differential equation, we could say, I don't know what the solution is, but I just know that it is some function of x. Are you with me? Let me repeat that. Given a differential equation, we know that the solution of the differential equation would be y equals some function of x. Okay, what is that y? What is that y equal to? What's that f of x equal to? Let's say I don't know. But what I do know is it's got to be some kind of a function of x. Now extend this. But we just saw that a function of x can be written as a power series. So we'll put these things together and claim that y, the solution of a differential equation, is a power series. And in fact, once you recognize that, there are some differential equations that you cannot solve. But the moment you take this approach of power series, you can find a solution. And there are some wonderful problems that have been solved based on this concept. So, ladies and gentlemen, I'll tell you, Taylor and Maclaurin series, this way of writing a function as a power series is incredibly important. And pretty soon I'll show you something else that is absolutely fascinating. Okay? Cool. Without much further ado, what in the world is this Taylor series and Maclaurin series? Having seen that a few functions could be written as an appropriate power series, we ask if we could write any arbitrary function f as a power series. That is, some f of x is equal to c sub n. Can we write it like this? Okay. To be able to answer this, we have to first identify what do we know and what do we not know. What are the known quantities and what are the unknown quantities? Let me do one thing. Let's just focus on f of x and the expanded version of it. Ignore the sigma notation in between. So, if I were to ask you, looking at f of x is equal to c sub 0 plus c1 times x minus a and all this, what do you think are the known quantities? In this case, okay, by the way, sorry. What's our objective? Our objective is to express a function, f of x, as a power series centered about some a. So what would be the known quantities and unknown quantities is what I'm asking. Let's start. Would we know f of x? Yeah, we would know. You have to tell me what function are we talking about, right? So for example, f of x is e to the x, or f of x equal to sine x, things like that. So f of x must be a known quantity. All right, what about a? Is a known quantity? Yeah, we can center the power series about whatever a we want. So a is a known quantity. What about x? Is x a known quantity? I don't know. Do you remember while we were talking about power series and all that, we said x is actually an independent variable. That means we know we can make it to be whatever we want within the domain, as long as x is in the domain of f of x, this function f. Yeah, we know x. So f of x is known, x is known, a is known. Okay, what is left? C sub 0. Do we know C sub 0? No, we don't. Do we know C sub 1? No, we don't. C sub 2? No. So basically we know everything except these constants C0, C1, C2 and so on. So the whole problem boils down to figuring out what these constants are. The moment you figure out what those constants are, which I submit, are dependent on what function you're looking at. What I mean by that is, if your f of x is e to the x, let's say, then c0, c1, c2 take on certain values. But on the other hand, if f of x is equal to sine x, those c0, c1, c2 will be different. Not all of them may be different. It's possible that C sub 0 is 1 in both the cases. But in general, C sub 0, the set C sub 0, C1, C2, all of this is different for different functions. The only thing is, can we figure out the values of those things? C sub 0, the constants. Okay. Now, how do we find these unknowns then, is the question. Okay. Here is where genius comes from. I can tell you how people find, but I want to give you guys a chance. Notice, I'm looking at, or I want you to look at, f of x is equal to this expanded version, C sub 0 plus C1 times x minus C and all of that stuff. From that, can you figure out how to find the values of the constants? Can you be clever about this? Okay, if you need to pause the video, please go ahead and do that. But can you find a way to figure out what those constants are? You may not need to find all of them. Let me give you a hint. You may not need to find all the constants in one shot. Just one constant at a time. Okay, let me be even more clear. Looking at f of x equals this expanded thing, can you find C sub 0? Right? Keep in mind, what are the known quantities? We know f of x, we know x, we know a. X meaning x is something we can make it to be whatever we want. Okay? Check this out. What if we let x be equal to a? Can we figure out, x is in a now, so what would the left-hand side become? F of a. Would we know f of a? Yeah, if you know f of x, you can figure out f of a. Right? So we know f of a. And then when we plug in x equals a, notice what happens. Every other term just goes to 0, leaving us with only C sub 0. So this constant C sub 0 is just nothing but f of a. You know the function f of x. You know what a you want to expand this about, what to make the center of this power series. And so evaluate the function at that center of the power series, and you get C sub 0. End of the story. How nice. So one constant down and just infinite more to go. That was funny. So let's get busy. Now, let's see how clever you are. How can you find, say, the next constant, C sub 1? Any thoughts? Okay. Now check this out. This, to tell you the truth, I had no idea when my teacher asked me that question. I was trying all kinds of, hey, what about, yeah, got it. How about x equals a plus 1 or something? Okay, if you let x equal a plus 1, we can of course evaluate f of a plus 1. But then what does this become? A plus 1 minus a is C1. Cool. This is 1 square is 1. So that just becomes C sub 0 plus C1 plus C2 plus C3 plus C4 all the way up to infinity. Interesting, but we didn't get the value of any particular constant. So that didn't work. So I racked my brains over it and nothing came up. And that's when this is the idea. So somebody said, okay, go ahead and take the derivative of f of x. So on the left hand side we have f prime of x. The derivative of c sub 0 is 0 because it's c sub 0 is a constant. The derivative of a constant is 0. And we get c1 times the derivative of x minus a is just 1. So c1 times just c1 times 1, which is c1. And if we take the derivative of c2 times x minus a, the quantity square, we get 2c2 times x minus a, and so on. Right? Now, I'm sure you saw this one. How do you find constant c1? Oh, plug a for x. F prime of a will cause all of this. When you evaluate f prime at a, then all these terms will go to 0, leaving you only with c sub 1. So, one more down. You want to find c sub 1? Just take the derivative of f and evaluate the derivative at a. Cool. So 2 down. And now I think the process is somewhat obvious. How do you find this c2? I'll take the derivative again, f double prime, and that turns out to be this, and evaluate that f double prime at a. And everything disappears, and all you're left with is 2 times c sub 2. Ooh, if we thought this would end up being c sub 2, no, we are wrong. It actually turns out to be 2c sub 2. So c sub 2 is nothing but f double prime of a over 2. Continuing the process, we end up getting and evaluating the triple prime at a. We get c sub 3 is f triple prime of a over 3 times 2, or 3 times 2 times 1. On purpose, I didn't multiply that and say that's equal to 6 because I wanted to see the pattern. And so f triple prime of a over 3 factorial. Well, was the previous one 2 factorial? Yeah, it is. 2 times 1, right? And so, what did we find? What? F of c sub 0 was f of a, right? What's up with my writing f of a over 0 factorial? How can I divide by 0? What is 0 factorial? 0 factorial by definition is actually equal to 1. So f of a over 1, wasn't that what we found? C sub 0 to be f of a? Yep, but I'm writing it on purpose as f of a over 0 factorial to be able to see a pattern. And what is 1 factorial? 1 factorial is also 1. So c1 is f prime of a over 1 factorial. c2 is f double prime of a over 2 factorial. c3 is f triple prime of a over 3 factorial. And based on that pattern, we can say c sub n should be, yep, you guessed it, f to the nth prime of a over n factorial. Right? So, what is it that we were wanting to do? Let's recap exactly right? We were trying to figure out how to write a function f of x as a power series. And what we needed to do was find the constants. The moment we find a constant c0, c1, c2, c3, we are done. We have found a power series representation of the function. Cool. So if you want to write f as a function, as a power series, this is what you do. And the way to calculate those constants, unknown constants, is by doing this one. N is a whole number. Provided what? Provided f is infinitely differentiable. Any idea what that's all about? Yeah. Notice how many constants would we have? Infinite constants, c0, 1, 2, c1, c2, c3, c4, c5, and infinite like that. But every one of those constants requires us to find that kind of a derivative. Like you want to find c sub 5, find the fifth derivative and evaluate it at a divided by 5 factorial. So you want the 100th term, you should be able to differentiate this 100 times. So for the infinite number of terms, we should be able to differentiate this function f infinite number of times. If you can do that, you can find the power series thing, representation of that function. Cool? That's the key. And this is what Taylor and Maclaurin, Taylor found. Hey, you want to write a function as a power series, then this is the way you can accomplish it. Okay. Now, there is another guy called Maclaurin. Maclaurin found the same thing. Looks like more or less around the same time. That's why they were both given the credit. And the only difference between Maclaurin series and Taylor series is Maclaurin series specifically works when a is equal to 0. So the Taylor series is a more generalized version. You can make a to be whatever you want, whereas Maclaurin series is when specifically a is equal to 0. You center the power series about 0. Okay? This is the idea. Cool? Now, based on this, let's actually get into figuring out the Maclaurin series and or Taylor series of different functions. Okay. The very first one I want us to look at is this function e to the x. If f of x is equal to e to the x, what is the Maclaurin series expansion of this? Right? So notice, please pay attention to this one. When can we say we are done? When we can figure out all the constants, c sub 0, c1, c2, c3 and all that. Right? Now, how do we find those constants? By f to the n of a over n factorial. A for a Maclaurin series is 0. Right? So to me, a good way to do this is draw a table and proceed in a logical fashion. What do I mean by that? Make a first column to be n. Excuse me. First column should be n. The second column should be f to the n of x. And the third column is f to the n evaluated at 0. If you're talking about Maclaurin, evaluate it at 0. However, if you're talking about a Taylor series, somebody has to tell you what a is, evaluate at that given a. Okay? And finally, c sub n is f to the n of 0 over n factorial. So first make a table and write down these 4 things immediately. Cool. Now let n take on a value of 0. Cool. So tell me, what is f to the 0th derivative of x? According to f to the n of x, that is, n represents the prime. What prime? If it says if n is 2, then we are talking about f double prime of x. So when n is 0, f to the 0th prime of x, what in the world does 0th prime of x mean? When we say, okay, let me put it this way. If n is 2, we know that we are talking about f double prime of x. How do we get f double prime of x? We take f of x and differentiate it 2 times. Right? Differentiate it twice to get f double prime of x. For f prime of x, we differentiate once. For f to the 0 of x, we differentiate it 0 times. We differentiate f of x 0 times. Let me be more precise. What do we mean by take the derivative 0 times? That means do not take any derivative, just leave the function alone is the idea. Cool. So f to the 0 of x is nothing but f of x. F of x is e to the x. Cool. Now f of 0, can we find f of 0? Yep, e to the 0 is 1. Can we find c sub 0 corresponding to n equal to 0? Yep, f to the 0 of 0 over 0 factorial, or we just figured out f of 0 is 1, so 1 over 0 factorial is 1. You agree with this? Take a good look at it, please. All right. Now, we are done with figuring out c sub 0, that is when n equals 0. Now, let's increment that to 1. Now, what should go in the second column? F prime of x, right? Can we figure out f prime of x? Yeah, f of x is e to the x, so f prime of x, we differentiate, we get again e to the x. Evaluate that at 0. F prime of 0 is equal to e to the 0 is 1. C sub 1, right? C sub 1 is f to the f prime of 0 over 1, f prime of 0 over 1 factorial. That is 1 over 1 factorial, which is just, I'm leaving it as 1 over 1 factorial, not simplifying it. Cool. F double prime of x is e to the x. F double prime of 0 is 1. C2 is 1 over 2 factorial. 3. F triple prime is e to the x. This thing is 1 over 3 factorial. Now the question is, have you seen enough to see a pattern? C sub 0 is 1 over 0 factorial, C1 is 1 over 1 factorial, C2 is 1 over 2 factorial, C3 is 1 over 3 factorial, C sub n therefore would be, yep, you are right, C sub n is 1 over n factorial. There we go. We have given a way of finding any constant in the expansion of Maclaurin series expansion of e to the x. Cool? Now, please pay attention to this. After you do this table and figure out these constants, it doesn't mean anything if you do not do the following. So make sure, after you're done with this table, you definitely do this. Write down this f of x is equal to c sub n, n equals 0, and the expanded version. Please be sure to, absolutely be sure to write both of this down. Okay? Had this been a Taylor series, replace this x with an x minus a. So f of x equal to sigma n equals 0 to infinity c sub n x minus a to the n, and that is equal to c sub 0 plus c1 times x minus a plus c2 times the quantity x minus a square, and so be sure to write all of that. Okay? Now, here, follow this up with the fact that here f of x is e to the x. So be sure to write e to the x. And substitute all the constants that you figured out. So c sub 0, we figured that to be 1. So be sure to write 1. Plus, replace the c sub 1 with what we found it to be, 1 over 1 factorial. So 1 over 1 factorial times x, or x over 1 factorial. C sub 2 is 1 over 2 factorial. Be sure to plug that in. 1 over 2 factorial times x square. You must write this thing. If you do not, then I would give 0 credit for the whole thing. If you tell me, oh man, I put in so much effort into making this table and I figured out all of this, I just didn't write the stupid thing, I don't care. Okay? You must write this original function, the power series f of x is equal to this, and then you figure out exactly what it should be for the function that is given. This is the money. I mean, I don't know why people wouldn't want to do this, because this is, after all, what we are trying to do. Write, in this case, e to the x as a power series, as a Maclaurin series. Okay? So once you write this, okay, all right, man, so what's the big deal? Now check this out. Your jaw should drop once I get done with what I'm about to get done with. Okay, can you tell me what an approximate value of e to the 0.1 is using this power series? Maybe I should have put it differently. I should have asked you this way. Okay, let's say you picture yourself at a time 300 to 400 years ago. 400 years ago. And there was no Maclaurin series expansion of anything. How do you find e to the 0.1? E to the 0.1 is e to the 1/10. That means it's the 10th root of e. Let's say you know the value of e to be 2.701, blah, 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 whatever it is. So all you need to do is find the 10th root of that e. Yeah. How do you find the 10th root of e? You will have a hard time doing that. So it's a pain in the neck to be able to find e to the 0.1. However, now notice, if you have this with you, the Maclaurin series expansion of e to the x, that assignment becomes a piece of cake. How? So that's why I'm saying find an approximate value. Yeah, you will see why I say approximate and not the exact value. Okay. All you need to do is go to this expression and plug x equals 0.1 in it. So we have 1 plus 0.1 over 1 factorial plus 0.2 square over 2 factorial and blah, 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 like this. Okay. Of course, we need to add infinite number of terms. Oh, come on. How can you add infinite number of terms? Yeah. That's why, notice, let's observe what these numbers turn out to be. 1, 0.1 over 1, 0.01 over 2, 0.001 over 6, 0. Over 24. Oh, wait a minute. So look at how small the remaining terms are getting. As you go further down, the terms are so ridiculously small. So it's perfectly all right if you want to say, I'm not going to consider terms beyond the 5th term, because yes, I need to add infinite number of terms, but the contribution of those is so small that I will try to ignore. And that's why we change the equal sign to an approximately equal sign here, because we are looking at only the first 5 terms, the sum of the first 5 terms of all the infinite numbers. Is that such a bad idea? No. See this. So this turns out to be this. And now, yeah, by the way, I think maybe written this way, you can see how small this very 5th term itself is, right? So you add up all of them and you get this. So e to the 0.1 is approximately equal to 1.105170. Isn't that cool? Now, I told you this would be jaw-dropping. I don't think your jaw dropped yet. But maybe now, if you use your calculator, go pick up a calculator and figure out what e to the 0.1 would be. I did that, and this is what I got. 1.1051709180 some blah blah. What did we get? 1.105170. So 1, 2, 3, 4, 5, 6. Seven significant digits matched exactly the first seven significant digits, because we terminated it at the fifth term. If we had added one more term, we would have gotten 9, and another term we would have gotten this 1 here. Now somewhat your jaw dropped. That's the idea. Well, the truth is, how do you think your calculator figures out e to the 0.1? Inside there is an algorithm built in which calculates the Maclaurin series expansion of it. Precisely whatever we are doing is what your calculator is doing. Right? That's the power of Maclaurin series and Taylor series. Okay, one more. Let's look at what's the Maclaurin series expansion of sine x. Once you understood the procedure for the previous one, e to the x, it's the same idea. Make a stupid table, n in the first column, second column, you tell me, second column, yep, f to the n of x, third column, f to the n, this is Maclaurin series, evaluated at 0, yep, fourth column, c sub n is equal to f to the n of 0 divided by n factorial. Right? Now get busy. Plug n equal to 0. F to the 0 of x is nothing but f of x is sine x. Evaluate that at 0, you get 0. So c sub 0 is 0 over 0 factorial. 0 factorial is 1. Do not panic. Oh man, you got a 0 over 0. No, I don't. I have 0 over 0 factorial, where 0 factorial is 1. So I have 0 over 1, which is equal to 0. Okay? 1. When n equals 1, we have f prime of x, which is cosine x. And so f prime of 0 is cosine of 0, which is 1. And c1 is 1 over 1 factorial. F double prime is negative sine x. Evaluated, you get 0. C2 is 0. Triple prime is negative cosine x. Evaluated at 0 gives negative 1. So negative 1 over 3 factorial. If you take the derivative again, the fourth derivative of negative cosine x, fourth derivative of sine x, you get sine x back. So this pattern actually repeats. What pattern? Fourth derivative is sine x, fifth is cosine x, sixth is negative sine x, and so on. That pattern repeats. So that means in this column, these values will repeat 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1. That pattern repeats. So correspondingly, these would be 0, 1 over 1 factorial, 0 over 2 factorial, negative 1 over 3 factorial, 0 over 4 factorial, and so on. So, there's something else that we notice. All these even terms, c sub 0, c even constants, c0, c2, c4, c6, c8, they're all going to be 0. And okay. All right. So once again, like I said, after you finish your table, the next thing that you want to do is write down this f of x equal to sigma n equals 0 to infinity, that thing, and be sure to write what that function is that you're dealing with, sine x in this case. So sine x equals, now plug the values of all the constants that you have. 0 plus c1 is 1 over 1 factorial times x, plus c2 is 0, so in that, write it like this. And of course, as you can see, you can simplify this and write it in a slightly different way. Right? And that means if you write this in sigma notation, we can write this as Notice only there are odd powers of x in this one. How do you get odd powers of x? 2n plus 1 will do the trick for you. Let's examine. When n is 0, what is 2n plus 1? Let me repeat that. When n is 0, what is 2n plus 1? 2 times 0 plus 1 is just 1. So we got the odd number 1. You plug n equals 1. Then 2 times 1 is 2. 2 plus 1 is 3. We get the next odd number 3. N equals 2. We get 5. Right? So by plugging n equals 0, 1, 2, 3, 4, 5, 6, and so on, we get odd powers of x. The 2n plus 1 would be all the odd numbers. So we can write it that way using sigma notation. And this is very powerful. In other words, what do I mean by this is powerful? Okay. Again, we can figure out what sine of 0.1 is, sine of 0.2 is, sine of any value. We can figure out, at least approximately, pretty decent approximation, not some stupid approximation, to a pretty decent approximation of sine of any value that we want. Okay. And in fact, I don't know if you bump into this in physics. Have you ever seen people say, well, when x is really small, sine x can be approximated as x, right? When x is small, sine x could be approximated to be x, people say. Does that make sense? Yeah, it does make sense. When x is small, that is, let's say 0.1, then x cube is 0.1, the quantity cube makes it 0.001, and you divide by 6. And this x to the 5 would be even smaller. So it seems reasonable to say that all the rest of these terms, the second, third, fourth, fifth, and the rest of them are ridiculously small. So we will say, nah, just ignore all of them and only keep the very first one, which is nothing but x over 1 factorial or x. So sine x is approximately equal to x, could be gleaned from the Taylor series or the Maclaurin series. Isn't that cool? So sine x is approximately equal to x when x is small, is the idea. Okay. Now, we've done Maclaurin series so far. Let's look at Taylor series. Taylor series, you must be given what A to center about, right? Somebody cannot tell you, hey, find a Taylor series expansion of f of x equals e to the x. Immediately your question should be, what is A? What do you want me to center the power series about? You should ask, right? So here, this is a nice problem, especially because it's so nice to be able to test the concept of Taylor series by an example like this. Okay, makes it a favorite one for any teacher to ask in a test. And very possibly I will ask you a question on something like this. What I might do is I might change this 2x cubed minus 3x squared plus x minus 3 to some other polynomial, and I might change this a. That's it. So understand this process clearly using this one, and we should be good to go. Okay. All right. Again, table nf to the n blah blah blah. But notice here we evaluate the derivatives at a, which happens to be 1, unlike in the previous cases where a was 0, right? So be sure to do that. And so when n equals 0, we have this polynomial. Evaluate this at 1. F of 1 is what we need to find. F of 1 happens to be plug x equals 1, and you get -3. So C0, right, C0 would be negative 3 over 0 factorial, or just negative 3. Now, when n equals 1, we have f prime of x. Can you differentiate f? Yeah. Turns out 6x squared minus 6x plus 1. Evaluate this f prime at 1. And trust me, you get 1. C1 is 1 over 1 factorial is 1. And at 2, you got 12x minus 6. And you figure out all these constants. Cool. Something interesting happens in this case though. The moment you go to the fourth derivative, we get 0. So f to the fourth prime evaluated at 1 is 0. So C4 is 0. What is the fifth derivative? Well, differentiate 0, you get 0 again. So 5th, 6th, 7th, 8th, all of them are just 0. Not only are the derivatives 5th, 6th, 7th, and 8th, and those derivatives are 0, automatically that makes the constant C sub 5, C sub 6, C sub 7, and them to be 0 as well. So all the remaining constants are 0. Only the non-zero constants end up being is C0 through C sub 3. Right? So a power series, what is supposed to contain infinite number of terms, in this case, it turns out, no, it doesn't have infinite number of terms. It has finite number of terms. That's entirely possible for it to happen like that. Okay, so like I said, always be sure to write down after you fill up the table, f of x equals sigma blah blah, and write this in the expanded version. Now plug in your constants, and also be sure to write that f of x. Right? Don't forget to write the specific f of x. Don't leave it as a generic f of x. Be sure to plug in what your f of x is. I have as a reminder, okay? I got the constants here. So f of x happens to be 2x cubed minus 3x squared plus x minus 3. So that is the left-hand side. Now let's plug all our values. So c sub 0, negative 3. C1 is 1 times x minus 1, like this. Isn't that cool? 2x cubed minus 3x squared plus x minus 3 can be written as a series centered about 1. Okay? And now here is a beautiful thing. I can ask a problem like this. Find f of 2 using both the original function and the Taylor series expansion. Okay, find f of 2 using both the original function and the Taylor series expansion. What's the original function? 2x cubed minus 3x squared plus. Can you figure out f of 2 based on that? Of course you can. Right? Plug to 2 for x and you get 3. Now do the same thing, but this time use the Taylor expansion. So plug x equals 2, and guess what? That also turns out to be 3. Coincidence? No. It's got to work out like that. If it doesn't, then you goofed somewhere, or I goofed somewhere. If I didn't get f of 2 to be the same value as the direct value, especially understand this, please. Our Taylor series in general is an infinite series, but in this particular case, this turned out to be a finite series. So we considered every single term in this one. So we must get the exact value, not the approximate value like that e to the 0.1 was, right? E to the 0.1 expansion, e to the x expansion had infinite number of terms. So we can only call whatever we get by considering only a few terms as the approximate value and not the exact value. That's not the case here. The Taylor series expansion of this polynomial turned out to be turned out to contain only finite number of terms. So the value must be exact, and sure enough, it worked out. Right? This is the beauty of Taylor and Maclaurin series. And in your book, there are a few problems, and be sure to learn how the whole thing works. Okay? What kind of problems could I ask? I might ask you, find the Maclaurin series of, since I did sine x, I could ask you cosine x. Okay? Or find a Maclaurin series of e to the 2x. Right? Find a Maclaurin series of e to the 2x. Or I could ask a problem on Taylor series, like I said, same kind. Here we have 2x cubed minus 3x squared plus x minus 3. I can change the polynomial and ask you something else. Or I could ask you for a Taylor series of f of x equals sine x, Taylor series, f of x equals sine x about a equals pi halves. So the center is pi half. Find out sine x centered about pi half, right? There could be a question like that. All right. Well, that wraps up this whole section, and in fact, the whole chapter. Folks, let me tell you, if you understood all the integration stuff that we did so far, and all this series stuff sequences and series stuff that we did so far, you have done an excellent job in calculus too. You should pat yourself on the back and feel proud of what you have accomplished. We are not done with the course yet. There are a few other chapters and all that, but they are not so conceptually difficult to grasp, and they are somewhat straightforward. They are also important, but these two are the main focus of this section, of this course, in fact. Okay? Alrighty.